All right, so let's talk about the question. This question is from Resnick and Halliday, and I will first explain you the behavior of tension as it occurs between two masses. So if you see this question, it has a lot of masses. It's a suspended system, which means the system is not moving. It's not decelerating, accelerating. It is mainly, it is stationary. And the good thing about this particular question is, you have a lot of parameters already given to you, which you need to work on, and then we will use those parameters. So let's first attack the question using one of the situations which is similar to this particular question, but the focus here is to understand how the tension acts between the two masses which are suspended. So you can see there are two masses, m1 and m2. The arrow I've drawn right now shows the weight of the mass m2. The earth is pulling it down with a force of m2g, which is a weight. And now let's focus on the tension in the string between the two masses. This is of interest to us. If you understand this particular part, you're done with this question, from Resnick and Halliday. Straightforward question, but you must be able to understand the behavior of the tension in this particular string. If you get this right, you're going to just make it. Now let me show you. You also have situations of horizontal masses, right? And then you have situation of vertical masses. This particular explanation is applicable equally well for the horizontal situation. If you pull a two mass system horizontally using a force, the tension between the two strings, and in the case of the situation I'm showing you, which is stationary one, which I called as suspended, is same, right? The tension between the two masses which are connected to each other always behaves in the manner the way I'm going to explain you now. And this is a point you must understand in general about tension itself. If you understand this, a lot of mechanics questions become easy for you. So I've just labeled tension. I have not shown the direction of the tension. I'm just showing you just a word, tension in the string. That's it. And similarly in the horizontal situation, you can see tension in the string. And I'm not talking about, I'm just saying there is a tension in the string connecting the two masses. Now if you pick up one of the masses, and let's focus now on the tension. Our focus is the free body diagram of second mass. I am showing you that this particular tension is pulling the mass m2 upwards. The tension in the string connecting the two masses is pulling m2 in the opposite direction of the weight. So m2g is downward, and therefore the tension in the string connecting the m1 m2 for m2 only is upward. So the string tends to pull m2 upwards, right? So if you look into this situation, there are two forces, m2g and t tension on the lower part, which is m2. I hope this is making sense to you. Let's talk about the situation of mass m1. If you see the string, the upper part of the string, which is touching m1, also is having the same tension. I'm again repeating, the upper part of the string connecting m2 m1, which is touching m1, also is working now, and it is working on m1. So when I said tension in the string, now I have split this tension into two parts, one acting on m2, which is pulling the m2 upwards, and then I'm referring to m1, which is pulling m1 in opposite direction, which is pulling it down. But let's come to the tension in the string, which is connecting m1 to the wall, right? So if you see the tension in the string, which is touching the wall, that particular string is pulling the wall downwards. The string which is connecting m1 with the wall is pulling the mass upward, m1 upward, and the wall downward. And now I have shown you the direction of tension in the string connecting M1 and M2. For M1, it is pulling M1 downwards, and therefore you can see this arrow, right? This is the arrow I'm referring to for M1. It is pulling M1 downwards. So the same string now, which we were referring to, tension in the string, suddenly has two parts to it, the lower part and the upper part. The lower part is pulling upwards, and the upper part is pulling the other mass downward. And same is the situation for the string, which is connecting the upper mass with the wall. I hope this is making sense to you. We are discussing only one thing right now, which is the tension, that part of the tension which is acting in the string but on two different bodies at the two different ends. That is what we are discussing right now, right? If you get this, then if you look into the question from Resnick Halliday, where you have multiple strings, one is connected, the topmost is connecting the wall and the mass number A, then subsequently A and B, B and C, C and D. All of this is based on just the framework or the knowledge we acquired as part of this small discussion, which is what is the tension in the two strings in this particular example, the tension in the string. That is what you need to understand. And a lot of students ask then what happens to the tension across the string. You have discussed the ends of the string, what happens to the tension in between the strings. Now, if you talk about the tension in between the string, it is zero because it gets cancelled. But this tension is only acting on the edges. It never acts through the string, right? So this edge, it is acting, pulling it down. This end, it is acting, but all throughout, other points on the string, there is no tension. There is a tension equal and opposite that gets cancelled, and the only tension which remains is at the edges of the string. And that is why when you tend to do these questions, you always draw the question, the tension at the edges of the string. So first step, get your concept clear on the tension part of it. That's the first thing you got to learn, right? If you learn this, then it's mechanics, right? Pure mechanics, which is what? Which is primarily working the free body diagrams. And free body diagrams, you already know, you're trying to apply Newton's second law, you're putting multiple forces on a single body, then the net force is equal to m into a. Since this is a suspended system, none of the accelerations actually exist. You will put all the a's to be zero. And so let me just rub all of this. I hope the scenario that I explained is clear in your mind. And now what we will do is we will start drawing the free body diagrams of D, C, B, A, and then use our knowledge we just acquired about the tension acting at the edges of the string, acting in opposite direction on different masses. That's your whole focus, right? I'll just rub this off and create some space for drawing. Let's start with the first, which is D, I think, which is a low-hanging fruit, pretty straightforward. The D is, the weight is acting downwards, and you already know the part of the string connecting D and C, T3, will act upwards. The net force is T3 minus M2G is equal to MD into A. You could write a reverse, M2G minus T3. Doesn't matter because the net force is zero. So T3. All right, so let's talk about the next one, which is C, right? So if you look at a C, just draw the diagram for C. C, if you look into this, and this is more distinct for you. C, if you look into, it is connected to two strings, the upper string and the lower string. Now, if you see the lower part, which is between C and D, so this is C I'm referring to. So this will get pulled in this direction. So T3 has reversed the direction for C. The direction for D for T3 was upwards. Here it is becoming downwards. And then if you look into the upper part of C, it is upward, right? And this is mcg, the weight of the C. So if you look into C, C is T3 plus mcg is equal to T2, right? I hope that you're getting this point that T3 is known to you, which is 9.8 plus mcg is equal to T2 is also known to you to be 49. So mcg is equal to 49 minus 9.8, and mcg is equal to 39.2. So mc is equal to 4 kilograms. I hope this makes sense to you. The way you did D was, D had the tension T3 acting on D at the edge where it touches the string in the upward direction, and the weight was downwards. But if you go to the same string, which is this string, but if you look into this particular aspect, right? If you look into this particular aspect, it's very different, right? It is acting just in the reverse direction. It's pulling C down, whereas it was pulling D up. I hope this question has become clear in your mind. What's happening in this particular question? If you like this video, please give me a thumbs up, subscribe to this channel so that you don't miss other. You have 2000 numericals done on this, and we're trying to improve the quality of our video and presentation as the time progresses, but you will see some remarkably good videos and solutions from numerous books. If you're in US, you're in Australia, India, Philippines, Portugal, wherever you see, you would love to see the solutions we do. We don't really focus on answers, we focus on making the students understand the real physics behind the answer. So let's go to the next mass now. All right, so let's talk about the next mass, and let's do the free body diagram of this particular mass. Very, very important for you to understand this. Not very difficult, it's pretty much the same stuff we're doing. Now the mass is B, and our whole focus is on the free body diagram. So you already know the concept. T2 is acting downwards, the mass is getting pulled in the direction, and T1 is going to act upwards, and therefore T2 plus mBg should be equal to T1. I have written T1 on the left with the negative sign to show the reverse direction. You know the value of T2, you know the value of T1, you can get the value of mB, right, which is mass. So you have one more equation, and you can find the mass of the B using this particular equation. I hope this is clear in your mind. Same concept as we applied for C is getting applied here, because B also has two strings connected to it. One upward and one is pulling it downward. There is a weight. Same equation, no change whatsoever when it comes to the mass B and C, right? Makes sense? Let's now focus our attention on A, where there is some peculiar different type of situation, but even this concept should be explained to you first before we even try to solve the free body diagram of A. So if you look into A specifically, it's different because the string in A first starts in a vertical direction like all other strings, but then because of the pulley it changes the direction, and this particular string then is connected to the wall on the left, and on the other side it is connected to A. Now when it is connected to A, it pulls A. I think I've drawn the a tilted line. Let me just draw a straight line to show the wall. So let's draw the wall again, and so this particular wall is getting pulled by the string towards it with a tension which is given in the question to be, I think it's given to be 98 newtons. So you see the line, which the longer top cord loops over a frictionless pulley and pulls with a force of magnitude of 98 newtons. Now when due to pulley the direction of the string changes, so the same tension of 98 newtons will now travel downwards. If it is pulling the wall on one side, it will pull the mass upward on the other side, right? So you know this now, how you have to work the strings. Even if there is a change in direction, the logic actually does not change at all. So the mass A is getting pulled upwards with a tension of 98 newtons. It has a weight MAG. So it has only two forces. One is a tension upwards, and mass, which is the gravity, bringing it down, trying to bring it down. It's a suspended system, no acceleration whatsoever. So let's write the equation of motion for, there is no motion, but that's the way we call it, for the mass A, right? I hope it is making sense to you now. and mass A is also connected to the lower part of the string, which has a tension T1 that also pulls A downwards, and therefore you can see the equation. The T1 is downward, A is downward, and 98 is acting upwards, right? So T1 plus MAG is equal to 98. This is another equation we are going to talk about. And you know the value of T1 already. It is given in the question. You can find the value of MA using that, right? T1 is given to be 58.8. So 98 point minus 58.8. So MA will also come to be 4 kgs. So this is the way we solve all the 4 equations. Each equation will give you the mass. And the basic concept that was used, I hope it is clear in your mind, was about how the tension in the string behaves at the 2 corners. That's most important for you to understand, right? So I hope this is something that you liked. Please subscribe to my channel, and really appreciate if you can give me some comments on whether you were able to understand what I taught you. That will encourage me to produce more videos. If you like it, please give me a thumbs up. And I'm going to give you some challenging questions to solve for yourself, right? And then we will release the videos for them. You can see how much of what I'm teaching you is making sense to you. But so far, so good, and we're making good progress. And thank you very much for your attention, and look forward to see you soon. All the best. Thank you.